to start recording. I hope everybody is doing really well today. I've had a phenomenal morning so far.
That's good. What is that due to? Something special?
How is homework going? Is your homework okay?
It's going okay for me.
Well, that's good. I hope it is for everybody. We are going to talk about inverse functions today. Not for the first time this semester. We're going to talk about them over and over and over again. But this will be the first time. Now, where? I don't understand. All right. There. Inverse functions. Inverse functions are basically so easy. And they're really interesting. So it's hard to beat that fact. We are going to look at the magic that goes into inverse functions. Some functions have inverses and some functions don't. We're going to talk about how you can tell which kind of function will have an inverse. Okay, but first we're going to talk about one of the really neat things about inverses that totally blows me away. Yes, okay, my mic and video are on, right? So everything is okay, and here we go. Take a swig of coffee. Okay. First thing I'm going to do, and this is where points come in, are important, you'll see. I'm going to find a bunch of points that are on this line. I'm going to let x equal -3, -2, -1, 0, 1, 2, and 3. And of course, that means I just put -3 in for the x, because that's what I'm letting -3 equal. -3, negative. It's not that easy, Barbara. Come on. You need more coffee. 2, -1, 0, 1, 2, 3, and now we're going to calculate 5 times -3 is -15, minus 3 is -18. 5 times -2 is -10, minus 3 is -13. 5 times -1 is -5, minus 3 is -8. 5 times 0 is 0, minus 3 is -3. 5 times 1 is 5, minus 3 is 2. 5 times 2 is 10, minus 3 is 7. And 5 times 3 is 15, minus 3 is 12. So I am going to graph the points x equals -3, y equals -18. Let's go down here. Okay, -3, -18, -2, -13, -1, -8, okay, -8, 0, -3, 1, 2, 2, 7, and 3, 12. Now, I actually care more about the points than I do about the line that's going to go through them. So I want to actually write these down. This is 3, 12. And this is 2, 7. And this is 1, 2. And 0, negative 3. And negative 1, negative 8. And negative 2, negative 13. And negative 3, negative 18. Okay, now that I have my points, I'm going to put a line through them. That'll do. Okay. Now I guess I need to okay, now I'm going to find the inverse of the function. I'm not going to find an inverse formula, not yet, but I'm going to graph the inverse because this is all the information I need. And this is so cool. Okay. The points on the inverse of the function are going to be 12, 3, 7, 2, 2, 1. Is this wild? Negative 3, 0. Negative 8, negative 1. Negative 13, negative 2. And negative 18, negative 3. Do you see that the points just reversed? So for instance, this point reverses, and instead of being 3, 12, it becomes 12, 3. So 12, 3. And 2, 7 becomes 7, 2. And 1, 2 becomes 2, 1. And 0, negative 3 becomes negative 3, 0. And negative 1, negative 8 becomes negative 8, negative 1. And negative 13, negative 2. Negative 2, negative 13 becomes negative 13, negative 2. And negative 3, negative 18 becomes negative 18, negative 3. Okay, so I'm actually going to take the time to write this because this is how people hundreds of years ago were able to graph the inverses without knowing what they were, without having the formula. They could find the formula for most things, but there's one thing we're going to study at the end of the semester that they could not find the formula for the inverse, but they knew it had to exist, and they could even find it and graph it by reversing points. So that is a wild, wild story in and of itself. When the way to find the formula was actually found, it was discovered by accident. And 2, 1, and 7, 2, and 12, 3. And we'll get this, and we will graph a line. These, ladies and gentlemen, are the graphs of two inverse functions. Now, inverses are important because they undo each other. Like addition and subtraction are inverse operations. Multiplication and division are inverse operations. Because they undo each other, they help you get back to where you started. And everybody wants to be able to get back to where they started, even if they don't want to go back, they want to know they could go back. It's like us. Here we are in the middle of a pandemic that just isn't going away. And we're hoping someday we're going to be able to get back to the way it was. Maybe we won't want to go back to the way it was, not all entirely, but we want to know we could go back. I think it's all going to be pretty different though, and I feel anxiety about that and excitement too. But anyway, enough of that. That basically is the story of inverses. But now as time went by, people discovered more and more. For instance, I'm going to graph the line in red, the line y equals x. So we'll have 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, 9, 9, 10, 10, and so on. That's the line y equals x. X and y are exactly the same. Okay, notice that each of these lines, oh, no, that's not going to work. I have to hover over my tablet. This line right there and this line right here are what we call equidistant. They're equally distant from this line, from the red line. We call that mirroring, mirroring. And the idea of mirror images is going to be very important very soon, okay? When we deal with something called transformations. Anyway, when whatever the two inverses are that you're graphing, they will always be mirror images of each other across that red line, y equals x. There are all sorts of these interesting little facts about inverses. Okay, let's get more into it. How do you know a graph is the graph of a function? Well, you use the vertical line test, and I'm going to do that right now. If I draw a vertical line, through that graph, the vertical line intersects the graph at one point. That means it's a function, and I could do it anywhere up and down the graph, and that line would touch the graph at only one point. Same here. So drawing a straight line is kind of difficult. I could do that anywhere along this curve. And that line would touch at only one point. So this is a function. All of these are functions because they pass the vertical line test. Where should I put this? I'm having trouble making decisions here. Okay. How about here? And here. And here. That never really gets straight. It looks straight on this drawing, but really they're not straight up and down. They're just close. I mean, the graph is just close to being straight up and down. It's really slanted. Okay, all of these are functions. All of them pass the vertical line test. Well, we have another line test, and here it is. This is the horizontal line test. Horizontal line test. Now my assumption is you remember the vertical line test, but if you don't, I'm going to write it now. Vertical line test. Okay, if you want to know if a function is one-to-one, first it's got to pass the vertical line test. It's got to be a function. Then we use the horizontal line test the same way we use the vertical line test. The horizontal line test has to cross the graph at only one point. For the function to be something we call one-to-one. Only one-to-one functions have inverses. So how about here? Yeah, how about I get a straight line? Okay, but that's true. This is a one-to-one function because it passes the horizontal line test. Over here, oopsie, it is a function. It passes the vertical line test, but it's not one-to-one because the blue line touches the graph twice. So this is not one-to-one. I'll go back and write it. This is one-to-one. I know it looks like this is laying down flat, but it's not. It's actually tilted. It's all of these things have been proven over the hundreds and hundreds of years. So this does pass the horizontal line test, and every horizontal line, if you look really closely, will actually only touch the graph at one point. And here, the same thing is true. This is the graph of y equals the square root of x, and it never doubles back down. It just keeps rising slowly. So it will never double back on itself. And here's the cube root of x, and this also passes the horizontal line test. And while this, the absolute value of x, does pass the vertical line test, it totally flunks the horizontal line test. So this function is not one-to-one. Here's the symbol for one-to-one. Okay, not one-to-one. And this function is not one-to-one. But this function is one-to-one, which means it has an inverse. And this function is one-to-one, which means it has an inverse. This function is one-to-one, even if that's not really totally horizontal. This function is one-to-one. And why we care, again, is that only one-to-one functions will offer you a way back home, a way back to where you started from. That's the value of inverses. They take you home, if you want to go. So one-to-one functions have inverses, and one-to-one parts of functions have inverses. Now, what do I mean by that? Well, between you and me, there's always a way to get what you want. So, some really smart person, not me, thought this up. Okay, here's y equals x squared, or f of x equals x squared, and it does not pass the horizontal line test. It's not one-to-one. But what if? I mean, here the domain is negative infinity to positive infinity. What if I were to cut the domain in half? What if I were to cut the domain and make it negative infinity to 0? Where this is the x-axis, here's 0, and here's the y-axis. And what if I were only going to use this part of the graph? I should have made it a different color. Let's use green. Then it would pass the horizontal line test. So you will see this done in your higher level math classes if you take them. If you're in a calculus class, and you might say now, oh, I'd never be in a calculus class. Well, I never planned to take calculus either. And then I suddenly found myself liking math. What do? You change your route in life. Or route, depending on where you come from in the country. Okay, so you could take a part of a non-one-to-one function that's one-to-one. So you could just take that part and work with it. And that happens sometimes. But we're not going to do that. We're just going to do straightforward. It's either one-to-one or it's not. Okay? Now, that's all well and good, but it's really time consuming to look at a function, find a whole bunch of points, reverse the points, and graph those. There must be a way to find a formula for the inverse, and that's what we're going to do now. We're going to do it 3 times. Here we're just doing it for linear equations, highest power 1. But as we go along, we'll be doing them for quadratic equations and square root equations and something called exponential equations and something called logarithmic equations. But except for the exponential and the logarithmic equations, we're just going to use the same exact steps we use now, as you will see. Here we go. It's going to be step 1, step 2, step 3, maybe step 4. I don't remember. You know, after a while, you stop thinking of the steps and you just do it. But in the beginning, it's important to keep your steps in order. So here we go. Okay, let me go back to black there. All right, step 1. Change the f of x to y. Then step 2, which is the most important. Are you ready? Because this one is totally different. Just like back here, where we changed our x's and y's around. We changed the order of the x's and y's. We're going to change the x and the y here. Okay. You have to do that step, which is the reason you have to change f of x to y. Now, step 3 can be a long process or a short process, depending on what you're dealing with. Step 3, solve for y. Okay, so I start with x equals 3y plus 2. I'm going to subtract 2 from both sides. 2 minus 2 is 0. That leaves me with 3y. And I'll have x minus 2. Now I'll divide both sides by 3. And in most math books, they leave it like this, which never made sense to me because this is still a degree 1 polynomial. It's a straight line, and that's not the way you write a straight line. Okay, so remember there's a 1 in front of the x. Our next step is going to be to do this. 1/3 x minus 2/3. Okay? Now, once we have y solved for, this is the fantastic last step. Step 4. It's a 4-step process. Are you ready? Here's the symbol for the inverse function. The whole thing, you don't take it apart, you don't say 1 over f of x, you don't do any of this. This is just a symbol, it's a code. It's a symbol in a larger code, and it means the inverse of the function. And all I'm going to do is copy down this. This is the inverse of the function. If you graph both of these, you'll see that they look like this. Not exactly, but they'll be mirror images of each other on opposite sides of the line y equals x. Okay, let's do it again. Practice makes perfect if you're practicing correctly. Step 1, substitute y for f of x. They're the same anyway. Then step 2, you switch the x and the y. I thought that was so weird. I still do. It's weird. X equals 5y minus 7. Now step 3, and again, here in these problems, it's just a few lines, but there can be problems where it takes almost a whole page, trying to solve for y. We're going to have x minus 7 equals 5y minus 7. Plus x, 5y minus 7 plus 7 to make 7 be a 0 over here. 7 minus 7 is 0. So I add it over here, I have to add it over here. Be careful. 5y equals x plus 7, and put your 1 in there right now. Divide by 5. Divide by 5. The 5's cancel. Y equals 1 1/5 x plus 7/5. And then step 4, once we have it in this form, we write what it really is, which is that it's the inverse of the original function. Here, the original function is f of x equals 5x minus 7. Its inverse is going to be f inverse of x equals 1/5 x plus 7/5. Ta-da! What do you think of that? I knew you'd love it. Let's do it one more time. Step 1. Oh, right now we've got f of x equals 13x minus 5. Step 1, we're going to say y, except I have to erase my y. I'm trying to train myself to not have my y take up 2 lines. Y equals 13x minus 5. Switch the x and y, that's step 2. X equals 13y minus 5. Now I have to solve for y. Okay, so I'm going to say x equals 13y minus 5. If I'm going to solve for y, I have to undo this subtraction at the end, so I will add 5, and that means I have to add 5. Not going to get fancy like I did in number 2 here. Okay, -5 plus 5 is 0. Let's even do it like this, just to make sure everybody can see what's going on. Okay, so we'll have x plus 5 equals 13y plus 0 is 13y. Then, if we follow the steps in the book, we divide both sides by 13. Actually, I noticed that the steps can sometimes be a little different. Not the steps, but whether you do this step or not can be different depending on who is doing the video. Boom, boom, the 13s can't cancel. You're going to have y equals, this is 1 over 13, 1 over 13 x plus 5 over 13. That's the inverse function. So now I have to write it as an inverse function. F inverse of x equals 1/13 x plus 5/13. And we have done this. How about that?
Miss Barb,
Yes, ma'am.
on the second equation, weren't we supposed to add another 7?
I did. I did eventually, but I kind of made it really sloppy. See, I added the 7.
But shouldn't it be 14 since we have to do?
-7 plus 7 equals 0. Is that what you mean?
No, so since we added 7 to the right side, don't we also have to do it to the left side?
We did, right here. It was x.
Okay, I thought it was part of the equation. My bad.
No, not bad at all. Thank you. You've got to keep me honest. That's your role here. Keep the teacher honest. Good. More discussion or more questions? Okay. See how much time we have. We have a lot of time. All right, we're going to start what we're going to do tomorrow. But tomorrow, next week, Monday. But we're just going to start it. And then I know we're going to have time. So we're going to go back and do one more thing I wasn't sure I really wanted to do here with the inverse functions. But I want you to see it. So there you go. But right now, let's talk about the greatest common factor, GCF. If we rewrite this, six is 2 times 3, and x squared is x times x. And then plus 3 times x. And let's stick a times 1 in there, because you're going to see that we need it. Now I'm looking at these two terms, remember from polynomials, this is a polynomial of degree 2, and it has two terms, so it's a binomial. And I'm looking at each term to see what's the same in both terms. And what's the same is there's a 3 in each term and an x in each term. And so I could say the greatest common factor of these two terms is 3x. Now, if we're factoring, if we're breaking things down, breaking expressions down into their component parts and saying, how did it get here? What had to be multiplied or divided to get this? Or was it just always this way? And we discovered that, well, this is kind of like genetics. They both have a 3x in them, so they're related. What we do is we pull that 3x out so everyone can see it. And then we put what's left over in parentheses. So in the first term, I have a 2 and an x left over. And in the second term, I have a plus and a 1 left over. And a way to check yourself to make sure you did it right is to say, okay, what if I took this 3x and multiplied it by 2x? Well, I would take the 3 and the 2 and multiply them together and get 6. And that's what I've got here. And I would take the x times the x to the 1 times x to the 1 is x to the 1 plus 1, which is x to the 2. And I've got that. And then I would take the 3x and multiply it by the plus 1, and that would give me plus 3x. So what I've learned by doing that quick check is that I factored this correctly, because you always need to get back where you started. If you factored correctly, you can always get back to where you started. Okay. So we're going to do it again. Here we have a trinomial because it's 3 terms. Highest power is 5, so it hasn't got a special name. We would just say it's a polynomial of degree 5. And I hear my dog coming in. Okay, so we are going to have a 4 times a 1 times an x times an x times an x times an x times an x. I could have broken the 4 down into 2 times 2, but I don't really have to because I looked ahead, and 4 goes into 16 and 4 goes into 8. So you're allowed to kind of use knowledge. Here 16 is 4 times 4. And it's going to have 4 x's. 1, 2, 3, 4. And then 8 is 4 times 2. And then there's an x. So I need to find what all 3 terms have in common. What do they share? Well, for sure they share a 4. And here's 1x. So can I find 1x in each of these? Yes, I can. I didn't really need that one at all, so I'm going to erase it. There. Okay, so each of these terms contains a 4x. 4x is my GCF, greatest common factor. Okay. Now, let's look at the leftovers. I have an x and an x and an x and an x. That's x to the 4th power. I have a 4 and an x times an x times an x. That's 4x to the 3rd power. And then, oh, look what I forgot. The 4 and the x. Okay, now I'm left with a plus 2. And then I'm going to double check. 4x times x to the 4th will give me 4 times 5x's, which would be x to the 5th. And 4 times x times this would give me 4 times 4, which is 16, and then x times x to the 3rd would be x to the 4th, and then 4x times 2, the 4 and the 2 multiply, giving me an 8, and then there's also an x, and that is what I started with right here. So that means I factored this down into its component parts. The GCF times the trinomial And now I'm ready to go on. Now, sometimes you're going to have terms that look like this. And you're going to be asking yourself, what do these have in common? They actually have a parentheses x plus 5 in common. What do they both have at the same time? That's what in common means. Well, they both have a parentheses x plus 5 at the same time. So I pull out the x plus 5. That is the greatest common factor. And what I'm left with is 13 minus 5. 13 minus x. Yeah, 5 is in there with the x. No, I wanted that one. 13 minus x. Now this is the factorization of that over there, where the GCF was actually a binomial. And then finally, this is a lot like those up there, except it's a disappointment too, because look, when I first saw that 6 and 12, I thought 6 goes into 12, I'm going to take 6 out of all these terms. And then I saw the 4. And I realized, okay, 6 does not go into 4. I have to change my plans. So let's go back to basics and break these down. This is going to be 2 times 3 times x times x times x minus 2 times, well, 2 times 3 is 6 times 2 is 12, so 2 times 2 times 3 times x times x. You can certainly use a calculator to help you break things down. Plus 2 times 2 times x. All right, now I can clearly see what these three terms have in common. This, incidentally, is a cubic trinomial. Trinomial because there are 3 terms, cubic because the highest power is 3. All right, I can see, I'm going to do this in blue. I can see first that each of these terms has a 2. And each of these terms has at least one x. Here's one x, and here's one x, and here's one x. And is there any more? Like, do any of them contain a 3? I mean, yes, 2 of them contain a 3, but I need for all 3 terms to have a 3, and it doesn't work. And this term has another 2 that can match with that, but I would need to have that extra 2 over here, and that doesn't work. So I'm stuck. 2 and x are as big as it's going to get for me. So I pull out the 2x, greatest common factor, and then I make parentheses where I'm going to put the leftovers. I'll have a 3 here. X times x is x squared, so 3x squared minus 2 times 3 is 6 times x, so 6x, plus 2. And there you have it. Notice there that this won't break down any further using the methods we've talked about so far. This is called factoring by GCF. And we're still going to be factoring by GCF on Monday. But doing a few more at least one or two more complicated things with it, other than just this. But this is the basics, and it's good for you to see this so that your brain cells can start thinking about how important it is to look at terms and ask yourself, what do they have in common? Okay, I am going to go back now to inverse functions and show you one of the proofs that two functions are indeed inverse functions. So I'm going to find an inverse really fast. How about f of x, I just want to put an x, equals x plus 3. And now I'm going to find its inverse. Three minus 3 is 0. So y equals, I wanted to make it super easy. And so our inverse function is going to be f inverse of x. Now, yesterday you learned about composing functions. There's a rule that says this. Two functions, f of x and g of x, are inverses of each other if and only if the following is true. Okay, so let me write this down. F of x and g of x are inverses of each other Here's a new symbol for you in math. If and only if. If and only if. That means absolutely only if. F circle G of X equals G circle F of X. That means they equal each other. And what they equal is X. Only X. So we're going to prove that what I have here, that they're really inverses of each other by composing them. I'm going to compose F with F inverse of X and see if I get the answer X. And then that's not enough. I have to compose the other way also. Getting my mind off what I'm doing here. And they both need to equal x, actually. So now we're going to do this. Okay, f of x equals x plus 3. We already know that. So f circle f inverse is really f with f inverse inside. That means f inverse of x is going to go in here. Okay? Well, what is f inverse of x? It's x minus 3. So that just means we're going to plug in x minus 3 right here and then add 3 because it was already there. And negative 3 plus 3 is 0. This is going to be x plus 0 or x minus 0, same thing. It's x. We're halfway there. F circle F inverse of x really does equal x, but it's got to be true the other way around. All right, so F inverse of x equals x minus 3. Now, F inverse of f, or F inverse circle f, is going to be F inverse with f of x in here, which means f of x is going to go in for x. Well, f of x is x plus 3 up here. So x plus 3 minus 3. 3 minus 3 is 0. That'll be x plus 0, which is x. So you have to get that result. And if you get that result, when you take two functions and you compose them both ways, and both ways you get x, that means they're actually inverses of each other. Yes, it does. I have nothing more to share with you. I'm kind of lost. Questions about all this stuff? You've learned the trick, haven't you? If you just let me go on and on, eventually I'll probably come to an end and let you out early. That's terrible. I'll just have to come over prepared with more information. But yes, I hope you have a great weekend. But if you have any questions, you can ask them right now. If not, remember that the great thing about inverses is they reverse the x's and y's. And that is a step when you're finding the inverse of a function. You reverse the x's and y's. And then you solve for y, and you get the inverse. If what you're dealing with is, a one-to-one function. Now, again, we're going to be dealing with this more as we go throughout the semester, and you're going to find there are a few more things that we haven't discussed that we will discuss, but it'll come when it's time, when we're dealing with things that are a little more complicated. Okay, so that was inverse functions, and just a peek at GCFs, greatest common factors, just to get you ready for what's coming, because we're gonna be factoring all week next week. I think probably all week next week, we're gonna be factoring polynomials and using them to solve quadratic equations. And then next week is the 4th week. The 5th week is your first test. So, okay. If there are no questions, I'll see you all on Monday. No more long holidays. I bet nobody's here except Myra.
I'm here.
Oh, okay.
Have a nice weekend.
Thank you, you too. Be safe. Oh, I have to there, save before I do anything else. That would be terrible if I lost it all. Oh. Okay, let me do this. Let me unshare my screen so I can see. Yeah. Hello, hello. I'm going to take off my sweater. It's starting to get warm now. It was a little bit chilly. It says I'm still recording. I thought I had stopped. I'm stopping now.